As I said, I think it's really useful to know that there's 3 types of questions. 2 of them we've seen, third one not quite, and it's enough that, and because now we're using derivatives to do this, whereas in MHF you're using the definition of a derivative, it starts to muck things up in your head about what goes where and what belongs to what. It'll make more sense when we look at some of the examples. So, one thing that can help is, like, in your mind, there's 3 types of questions. This one's this type. This one's this type. This one's this type. And try to have a sense of, you know, there's similarities between all of them, but how are they different and how do you do each type? Okay? And sort of keep them organized. And it gets trickier when the questions change a little bit. Most of the practice today, I think, is very straightforward, but throughout the unit, these kinds of questions will come up again and again, and some of them are a little bit different, and that's enough that if you don't understand which type you're doing, or if you get confused about that, then you're going to do it wrong, okay? So just keep that in mind. Okay. So here we go. Let's try the first one. This one is not new. This is the same as before, but we're going to use the new way of doing it with derivatives. So again, we did this kind of a question. We wouldn't have done it with this expression, but we've done questions like this, and we use the difference quotient. Limit as x approaches a of f at x minus f at a over x minus a. And we would have subbed in, we would have found f, like this would be a, right? And that would be f at a. If we weren't given it, we would solve for and find it. We'd sub into the expression, do whatever work has to be done, whether it was rationalizing with the conjugate or factoring or whatever it is. Do whatever work has to be done so the x minus a part factors out, and then work like the indeterminate limit. Again, last semester we didn't call it that, but and then we could sub in and solve. That's how we would have done it, because we knew that the difference quotient is a way of calculating the instantaneous rate of change, which is what a slope is. A slope of a tangent is an instantaneous rate of change. But now we have a new way. We have this thing called the derivative, which is a simpler way of calculating the difference quotient, coming up with an expression for it, and then subbing in. It's way less work. So in this case, this is a product of 2 things. We don't know how to do that yet. We're doing the product rule on Monday. But in this case, the easiest way, even if you did know the product rule, this is if you take one step and simplify by expanding the x minus 4 through. So this becomes x to the negative 2 minus x to the negative 4. And then find the derivative, y prime. Whoops. Oh, yeah. Okay, sorry. Getting ahead of myself here. So bring the negative 2 up front. X, decrease the exponent. What do you think I do now? We could. We don't have to. You could. Yeah, so sure, let's do it. Very nice. We're going to sub in the 2 for the x, so at x equals 2. So whether you did this first or after, it'll be the same thing kind of thing. I'm going to bring this negative out front, negative 2 over 2 cubed, and I'm going to change the 4 to 2 squared over 2 to the 5th. So I can simplify. So that's negative 1 over 4 and 1 over 8. Negative 2 over 8 plus 1 over 8, which is 1 over 8. So at that point, which that point had better be on that curve, in this case, we didn't use the 5 over 16. Sometimes you will, sometimes you won't, depending on the question. In this case, we didn't have to. But we're assuming the 5 over 16 is correct. And but at that point, which is on the original curve, the slope of the tangent to that point has a slope of 1 over 8. That's what that means. I want to remind you, because this is where it starts to get tricky. Remember when we looked at this? So here's the original function. And now we know a little bit more about all of this, how if the original function is a parabola, its derivative will be linear, right? Original function is quadratic, degree 2. The derivative will be degree 1 linear. And this point and this point, so this is a point on the original function, this is a point on the derivative function. They share the same x value. The y value of this point is the slope of this tangent, the slope of this line. So when I subbed x in to the derivative, because this is a function in and of itself, and this is where you start to get confused. Which one am I subbing x into to find what I need to find? Do I sub x into that or do I sub x into that? And if you get it wrong, it's wrong. So when I sub x into the derivative, it calculates a y, but that y value corresponds to the slope of the tangent on the original function at that point. Okay? So that's how that worked. That one's done. Pretty easy, pretty simple. Yes? Negative 8 over 1 over 8. Yes, thank you very much. Yeah. Any other questions? Okay with that? All right, let's try another one. So this is one that's new. And we need to remember how to find the equation of a line. Which you probably have since grade 10 you do it. Grade 9 you learn how to do it. Grade 10 you do it. And then not so much in grade 11 or grade 12. Who remembers the formula? Now there's two formulas that you could use, but there's one that's for finding equations of lines. Who remembers what that formula is? Anyone? 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 You're all just busy writing down the question. Formula for the equation of a line. So you can use y equals mx plus b. There's actually a bit of a simpler way. It'll save you a few steps. If you want to use y equals mx plus b, you can. Use y equals mx plus b. You have to have a point, which is your y and your x, and your slope, which is your m. Solve for b, take b, sub it back in, and then if you're putting it in standard form, you'd have to rearrange to put it in standard form. And it's the subbing back in part that we can skip. Let's see if you recognize it when I write it down. Who remembers this? Y minus y1 equals m times x minus x1. Remember that? No, some of you haven't seen it, yeah? Yes, some of you do remember that. Okay. I think this is the easier way. If you haven't seen it before, it's way easier than anything else we do, so it's not a big deal. But you can use the other one if you want. Just make sure you know how to do it. Don't take it for granted. Don't make grade 9 mistakes and not be able to properly find the equation of a line. Okay? Formulas, a really useful way of thinking about a formula is what's the input that it needs in order to give me the output, and what is the output? That's something we always think of in terms of formulas, right? What is the output? What does this formula give me? And that's how we choose what formula to use under what circumstances. But we also always need to know what the input of a formula is. And back in grade 9, this is probably the hardest thing that you do, is finding equations of lines. And the input of this formula is a point and slope. A point on the line that you're trying to find the equation of, which in this case is a tangent, and the slope of the line. So in this case, that's the slope of the tangent. We're doing some straightforward examples today. As I said, most of the practice is straightforward, but throughout the unit, there will be some other questions that maybe give you, like, what if it'll say something parallel to this line, or perpendicular to this line, or parallel to the slope of the tangent, but with a y-intercept of something else, right? Like, it'll give you different information. That's where the problem solving comes in. So you have to always be thinking of, is this a point on the line I'm trying to find the equation of? And is this the slope of the line I'm trying to, or is this some other slope that's related or whatever? So just don't get confused about that. That's a hard part of grade 9. Hopefully it won't be it's not too bad, I don't think, in this course. So we already have a point. The tangent to the curve to this curve at this point also goes through that point. That's what a tangent is. That's the only place in that location. Tangents can cut functions other places, but there's the only location in this place, in this vicinity typically, that it touches that curve. So this point is on the line we're trying to find. So we already have a point, so we have to find this. And to do that, we're going to use the derivative. That was a lot of explanation for something that may have seemed obvious. So now what are we going to do? Yep, sub x, the x value that we're trying to find into, whoops, that should be derivative, into our derivative to find the slope of the tangent at that point. Again, we are asked to find the equation of a line. The formula for the equation of a line requires slope of the line and a point on the line. So we've got a point and we've got a slope. So now we can go ahead and use this formula. The reason why this formula is nice and a little bit fewer steps than y equals mx plus b is because once I get here, it's 1 or 2 steps, probably 2, to get to the end. Whether it's standard form or any other form, it's very quick to get it exactly where you need to get it to. Okay? But if you want to use y equals mx plus b, go for it. So we'll remind you what standard form means. So I'm going to expand and move everything to one side. 8x plus y minus 7 equals 0. Standard form is all integer coefficients, fully simplified, equal to 0 usually is how we do it. Everything on one side of the equal sign equal to 0. Okay. Any questions about that? Okay, let's try another one. I'm going to let you get those ones started. Okay, so look like people are on the right track. You should get 1/2 as the slope, I believe. So I'm finding the equation of a tangent. So I use the slope of the tangent and the point on the line. And again, this is the power of this formula. When I have a fractional slope in one step, I multiply by 2 on both sides, technically, obviously, I hope. But what that does is the 2 distributes over here. I get 2y minus 8, and it gets rid of the fraction 2 on the bottom there, and this just ends up being x minus 1. Collect everything to one side. X minus 2y plus 7 equals 0. So from subbing into the formula, it's pretty much always 2 steps to get to the answer. It's just a little bit less work than y equals mx plus b. Technically, if it says standard form, no fractions. That's what it means, basically. Okay, any other questions? We're going to do one more. So we did questions like this in MHF. Now this is pretty straightforward. But what do I do next? What's the next step? Yeah, in the first example we did, you sub in for x and solve for the slope, which is y prime. In this case, you're given the slope, so you sub that in for y prime. Again, we did this before. And this says find the points. This is a parabola. How many places will the parabola have a slope of 8? The algebra will work it out for you. But if you already know how many answers you should get or you might get or you're likely to get, then that puts you in a better position to be like, I think I got the wrong number of answers. Sometimes it's going to be more than 1 point. And there's an easy algebraic mistake that people always make where they miss it. So the algebra will fit it, but how many points should we get for this parabola? Just one, that's right. In this case, a parabola will have every slope somewhere but only in one place. So for a parabola like this that opens up, the positive would be somewhere along here. But if it was cubic, I would have 2 places. 1, 2, where the slope is parallel. In this place, I would just have, quadratic, I would just have 1, right? So we're expecting that. Again, the algebra will work that out when I put 8 in here. This is a very simple linear equation that we have to solve. It has one answer. The mistake that people make is when when it's quadratic and they take the square root of both sides and they forget to do plus minus square root. Okay, so this is 10 equals 10x, x equals 1. Done? No, we're not done. That's right. What do we have to do? Find the y. So how am I going to do that? Again, if you don't understand what you're doing and you get confused, you can make a mistake here. That would just find an intercept. We don't know if that's what we want. Why the original? Which is, yeah. But this is what people do, is when they get this x value, they don't know where they're putting it. Okay, so I'm going to make a couple notes here. Y prime equals 8, that's the slope. And then here, sub x equals 1 into original equation. And since it asks for a point, you should state it as a point, not just leave it as x's and y's. Find the point or points at which the slope of the tangent to the given curve is 8. So for that parabola, that point, which is on the original parabola, is where it would have a slope of 8. Again, if you think about that visual, it makes sense. But again, there are common mistakes, subbing x into the wrong equation, or setting the wrong equation, like subbing in for y in the wrong equation. If you're subbing in for slope, you got to put it in the right place. Any questions about that? I want to talk about one other thing. This is the practice that you'll get to in a little bit. We're going to do a proof first. But question number 1, we didn't do an example like that. It's just asking you to find the derivative. So notice that it says ds by dt, and these are all equations in terms of s and t. So if you're finding ds by dt, you're just finding like s prime. And this is something we actually kind of already know, but I'm going to point it out even more explicitly. It's a very important, useful application that we'll see maybe a little bit in this course. And if you are in physics or engineering or maybe other sciences in university, absolutely this will be something that you're doing fairly often. Remember when we did those questions in MHF where you have a parabola representing the height of a ball that's been thrown or something? And then, so that's like a distance or a height, right? But that's a height is still like a distance that's being covered. And when we found the instantaneous rate of change of the ball at a particular point, we were finding what? The speed of the ball. What's the rate of change of a distance? It's speed, right? So it turns out, if I have a function that represents the position of an object, which also is similar to like distance, okay? Its derivative is a function of the object's velocity or its speed. When you take the derivative of a position function, the derivative is the function that represents its velocity at all those instantaneous points. And I think, in fact, if you look at some of the formulas you use in physics, you could work out how one is the derivative of the other. It's interesting. So that's all it's asking you to do, is find ds by dt, which is actually v velocity. Very important application. What would the derivative of velocity be? What is the rate of change of velocity? Acceleration. If you're accelerating, your velocity is changing. You could accelerate over a period of time. Again, that would be an average rate of change. That would be a slope of a secant line. If you had a velocity curve and you found the average rate of change, that would be average acceleration. But you can have instantaneous acceleration at a point. So you take one derivative, you get velocity. You take the derivative again, not something we've talked about, but the derivative of a function is a function. Of course you can take its derivative. It's called the second derivative. It's something we will be doing a lot of. That would represent the object's velocity. So that's useful stuff.